Hi everyone. Just going to give a brief overview of what we do at the Plant Health and Environment Lab, just in case you're not familiar with this part of MPI. So our lab does biosecurity and surveillance diagnostics. We also do import and export testing, which means that if a suspect ceratocystis sample was found during surveillance, we would be the one testing it, as well as we test all the imported plant material that could be potential hosts for ceratocystis to make sure that they're free of this unwanted pathogen. And in addition to that, we provide scientific and technical advice, both internally and externally, conduct training, and our lab also provides post-entry quarantine. We have a facility on site. So we do contribute to the strategy of MPI for protection and prosperity. So our lab in Auckland has nearly 70 staff. We have 4 teams. There is mycology and bacteriology, my team, entomology, virology, and botany and post-entry quarantine. And our lab facilities provide full setups for DNA-based testing, morphological testing with different microscopy setups, as well as collections for insects, fungi, viruses. So we are pretty well equipped. So ceratocystis diagnostics at PHL, at our lab. A year ago, it was what Aselina just described to you. So we get a sample, we do this carrot discs, we did also use organic ones. So organic carrot bedding, and then we try to isolate the fungus. If we find something, we will then proceed with DNA analysis to determine what it is. So that would take 2 to 3 weeks if we found a suspect ceratocystis, and 1 week to rule out if nothing was growing. It still took us 1 week to know. So that's quite a long time. And as Aselina also mentioned, it is not that reliable method. There is a chance that we won't detect it. So ceratocystis was a priority for us for testing imported plant material to make sure we are confident that the material really is free of the pathogen. So just repeating a little bit what was just mentioned. So ceratocystis is something with certain morphological characters, a big group of things. I've just made a visual thing for you. There used to be this big group of organisms that were used to call ceratocystis. After people started looking at the DNA and determining what is really closely related and what is not, we now have something more specific that's ceratocystis. And all those other things in that bigger circle are now called something else. And even within ceratocystis, there is this cluster of things that were called ceratocystis fimbriata, but there is this taxonomic debate there. Ceratocystis fimbriata really is something very specific. The Ohia death pathogen, for example, in Hawaii, often is called ceratocystis fimbriata. It is not ceratocystis fimbriata, it's different species. So we need, at MPI, we need to be ready for a broad range of ceratocystis, not just ceratocystis fimbriata, not just the kiwifruit isolate. We also care about Metrosideros, we care about Prunus, which also has another ceratocystis species. So our approach was to develop a DNA-based method that would detect everything that's in the ceratocystis, and we take the current ceratocystis approach. So as part of operational research from MPI, we have a project where we focus on developing new tests, and ceratocystis was our first target for that project. It took us nearly 7 months to get the assay, but we are here now. On that picture there's Karthik, the scientist who is working on the project full time, 7 months to get the assay. So we used 33 different species of ceratocystis, 55 isolates we obtained from overseas, and we developed a PCR assay, real-time PCR assay. So basically it's just a method that detects DNA. It's really sensitive and it's really fast. And that's what it looks like. We will extract the DNA from the suspected infected sample, mix it together with all sort of reagents, put it in a machine, start a program, and we start seeing some sort of curves. If those curves pop up here, that means ceratocystis is present. If the line stays flat, it means no ceratocystis is found. So we can use this directly on plant material. If ceratocystis is present, we will then have an extra step to find out what ceratocystis is it. So there is another assay we have developed for further DNA analysis and sequencing to determine what it is. So just to sum up, what we have is this assay that's able to detect all known ceratocystis species. It's sensitive enough to detect pathogen from non-symptomatic plant tissue. So we made infections in plant material. That's just an example of a stem here that was inoculated here. Maybe you see a little bit of brown here. We obviously detected ceratocystis from here, but we also found it from here and here. So where there are no signs of disease, we can still pick up the pathogen, which is great news for testing imported material, which obviously wouldn't have any signs. We also can detect the fungus with this assay from naturally infected Ambrosiae beetles. So if there was a vector that would be carrying ceratocystis, this assay would catch the fungus. And we have tested this assay in another lab in New Zealand as well as in Australia, and they got very similar results. So it is a reproducible and a good assay. So basically, if we were here a year ago, then today, when we get a sample, we go straight for DNA extraction. We run our assay. If nothing is found, we can declare negative. If something is found, we do a little bit of more work to determine what it is. But the time frames are significantly reduced. So it will take us 1 to 2 days to get clear, nothing found, and 3 to 5 days to know what it was, if there was an infection. So it's quite a significant drop in time compared to the carrot method, and there is very big difference in susceptibility and reliability of the methodology. So we are using this assay to screen imported plant material, as I already mentioned. We already do that, and we would also be using it to test suspected infected samples, which would get from general surveillance, for example, you guys, targeted surveillance, or from incursion and response. So just would like to thank Karthik, who's the scientist who did most of the work developing this assay, my team, MPI plant imports and risk assessment teams, and the operational research who funded all this project. And we really thank Mike Wingfield from South Africa for sending us lots of isolates, and Mark Anderson for doing the testing to make sure it works in another lab as well as Julie Pattemore and Joanne Mickey from Australia who did the testing over there at the Mickleham PEQ facility. Thank you.
Thank you, Merje.